Good afternoon, everyone, and welcome to this webinar, which is part of the dissemination activities for the NERC Environmental Risk Infrastructure Innovation Program. Today's webinar will focus on the risks and challenges associated with geological hazards. If you wish to communicate with us during the webinar because you have a question for one of the speakers or you experience any technical issues, please use the question section on the control panel on the right-hand side of your screen. Also, just to let you know that the presentation and slides and recordings of today's webinar will be available on our website after the event. So, my name is Ciro Daleu, I work for Syria. We are the program coordinator for the ERIIP. We facilitate academic and industry collaboration, support and monitor funded projects, and we manage the dissemination of the program outputs. Today with me there are Paul Mellon from Transport Scotland, Jonathan Chambers from BGS, and Simon Mudd from the University of Edinburgh. Paul will provide an overview of the challenges to the transport sector associated with geological hazards, while Jonathan and Simon will provide an overview of their ERIIP funded projects. Before handing over to Paul, John, and Simon for their presentation, I just want to give you an overview of the ERIIP program. Apologies if you've already seen these slides before, but we thought it would be a good idea to provide this overview for those of you who don't know much about the program. So the ERIIP program is a $5 million 5-year program that brings together the Natural Environment Research Council and infrastructure owners, operators, policymakers, and regulators. The program funds innovation and translational projects which use environmental science to identify, quantify, and manage environmental risk. The program is structured around 3 themes. Theme 1 is identifying, understanding, and quantifying environmental risk to the infrastructure system. Theme 2 is likelihood, effect, and impact of multi-hazard combination on the infrastructure system. And Theme 3 is dealing with uncertainty in design, operational, and investment decisions. Of course, the 3 themes are interdependent, are linked between each other, and they allow us to look at infrastructure as a system of systems. So the program is, as I said at the beginning, is translation focused, which means that it focuses on the use of existing science research, which translate existing science into industry relevant knowledge, methods, and tools. All projects must have project partners related to the UK infrastructure. So, as I said before, infrastructure owners, operators, or regulators, or policymakers. Each proposal should demonstrate how science can be applied to develop a solution to address the personal challenges related to the environmental risk. Also, they should demonstrate the impact and benefits that the project will have on the project partners as well as then the wider industry. The program is steered by an industry community, which is made of the organization that you can see on the screen. These are the ERIIP members. Although all the projects, as I said, must have industry partners, it's worth noting that the industry partners don't have to be necessarily members of the ERIIP industry community, so not necessarily ERIIP members. In terms of what has been done to date, 3.6 million have been awarded to 23 organizations across the UK. 142 researchers are involved in the funded projects, and 78 industry partners are involved in one or multiple projects. Finally, just to let you know that the 2017 funding call is now live, is open. It was launched in February 2017. The next step of the funding call would be the brokerage event in March, where the industry and academia would meet and would have the opportunity to discuss research priorities, proposals, and ideas. Following the brokerage event, there would be a time for the academics to prepare their expressions of interest and submit them by the 3rd of May 2017. And following the expressions of interest stage, there will be the full proposal stage, which closes on the 11th of July 2017. If you want to know more about the funding call, you can visit the ERIIP website, which you can see on the screen. Without further ado, now we'll hand over to Paul Mellon, who is a chartered engineering geologist. He has previous experience in both private consultancy and local authority. He joined Transport Scotland in 2008, and as a geotechnical manager, he is responsible for developing geotechnical module for Transport Scotland's trunk road asset management system. His presentation will be on the Transport Scotland vulnerability to geological hazards and climate change, and on Transport Scotland proactive asset management system, which uses techniques to target cost-effective interventions. Now I hand over to you, Paul.
Now, Scotland is blessed with a rather interesting landscape, but that combined with climate, which has a very high rainfall on the western side of the country, makes Scotland's trunk road network vulnerable to landslide hazards. This is Glen Ogle, which was one of our more celebrated ones. The next slide shows the fact that the first landslide that you saw in the previous slide is the one in the distance, and when the traffic had been halted by that, a second landslide came down behind the traffic queue, mercifully missing the tail of the queue, and we had to make a very concerted effort to rescue the stranded drivers between the two landslides. So that incident and a number of other incidents about the same time led us to look very closely at landslides, because the Scottish trunk road network, away from the central belt where the traffic flows are very high, in the highlands and the southern uplands, the primary role of the trunk road network is connectivity, to bring a very dispersed settlement pattern together, and particularly to connect with the ferry ports on the west coast, which are the lifelines to the islands in the Inner and Outer Hebrides. So following on from the landslides at Glen Ogle, and also at Rest and Be Thankful, we initiated the Scottish Road Network Landslide Study. This was managed by TRL, Transport Research Laboratory, and drew in material information from DGS, and the Met Office and so on, and produced a risk assessment to highlight those areas of the Scottish trunk road network which were most vulnerable to landslides. And just as an illustration, we'll look at one of them. This is the A83 on the approach to the Rest and Be Thankful, which is the pass, the high point off to the left of this picture. But there's a large slope here which is very prone to failures, and we've listed here all the failures since 2007. So you can see there's a significant issue here, and this is a vital link to both ferry ports and a range of remote communities. On the basis of the landslides report, we've undertaken a series of management measures, the first of which is monitoring. On the left, we've got a weather station, which returns primarily rainfall data, which is proven to be the most useful. We also installed at various times arrays of piezometers and tilt meters, and it has to be said with mixed benefits from those. But as well as monitoring, we've also undertaken some hard engineering to prevent landslides reaching the road and therefore causing disruption. Obviously, this has to be targeted, so there is a risk assessment process involved in positioning these, but the things like the landslide barriers do work. However, from a management point of view, it is awkward because you've then got to close the road to empty the debris out of the landslide barrier. We are now turning towards a slightly different approach in that we're using patch pits, which are less visually intrusive and are easier to manage when they do become full. And we're also looking at other engineering approaches, soft engineering like planting as a potential mitigation hazard. The third strand to management is in the operations. So we've introduced what we like to call wigwag signs, which are activated by triggers based on rainfall or intensity of rainfall. And these activate the signs, the flashing lights, and there's been an education process for regular users of the road so that they understand what the signs mean and what they should do. And this is accompanied by landslide patrols who patrol up and down the road looking for instability in the slope above and are empowered to call in the police and close the road if they feel that the risk is too much. I should also mention that as well as landslides, we have a significant issue, potential issue from rock falls. And we've carried out a very similar risk assessment approach to identifying the high priority areas for rockfall risk. And we've been carrying out a program largely of hard engineering of bolting and netting to, again, mitigate the risk to road users. So just to wind up, the ongoing tasks that we're undertaking are firstly to understand the mechanisms and to understand what triggers we can use to implement particularly management operational processes. And as I mentioned already, rainfall and intensity of rainfall have proven to be the most useful triggers so far. We're reviewing our risk-based prioritization. We're carrying out detailed risk assessments where that is appropriate of the higher risk areas. We're carrying out targeted hard engineering, as I've shown, in terms of the landslide barriers and now patch pits and potentially other engineering solutions. And we're always reviewing operational procedures. But the tie-in with the triggers would be, I think, of great value to us. And as Sergio mentioned in his introduction, I'm now trying to integrate the landslides and rock face management with our general Transport Scotland roads asset management system. So to conclude, I suppose our vision, shared I imagine with a lot of other infrastructure owners, is to have a proactive asset management system using appropriate techniques to target interventions cost effectively, and therefore we have an interest in any developments which can help us to achieve that vision. So thank you very much. Over to you, Sergio.
Thank you, Paul, for setting the scene and the context for the webinar and for the following presentation by John and Simon. So I will now hand over to Dr. Jonathan Chambers. He's the leader of the geophysical tomography team at the British Geological Survey. He is also an Earth Knowledge Exchange Fellow for Infrastructure and the honorary lecturer at the University of Nottingham. His research has a strongly applied and industrial focus, and it is concerned with the development of geophysical, geotechnical, and environmental monitoring methodologies, and their application to groundwater and slope stability problems. He has been working with industry partners for several years to develop a new geophysical system for monitoring earthworks with the transportation and utilities sector. So I will now hand over to John.
Good afternoon, everyone. I hope you can all see my screen. So yes, I want to introduce to you the proactive infrastructure monitoring and evaluation system that we've been developing within the ERIIP programme with a number of partners from within BGS and external stakeholders, as indicated on the screen here. In terms of the key drivers for this work, really it's vulnerable UK infrastructure. So much of infrastructure, particularly in transportation, so rail and canal, was developed a long time ago, hundreds of years even, and very poorly engineered. When you combine this with a greater prevalence of extreme weather events, then we've had serious problems, and even more modern infrastructure experiences significant challenges. And here we have some recent examples from just the last few years showing this in the UK context, with lots of failures resulting from heavy winter rainfall events. Now, there seems to be an increasing awareness within industry that remote condition monitoring has something to offer beyond simple walkover surveys or surface inspections. There's a recognition that new monitoring technologies can contribute to asset management, and that's really where we're seeking to develop PRIME. So just to introduce the technology specifically, PRIME is a low-cost, low-power geophysical remote condition monitoring system designed for monitoring earthworks and natural slopes as well at risk of landslide, with the aim of giving us early warning of failure events. So the project, the technology combines a technique called electrical resistivity tomography, quite a well-established geophysical survey technique, with combining this with telemetry, web portal access for intelligent monitoring. And really the concept here is that we're applying diagnostic imaging methods, very similar to those used in medicine, for example, to non-invasively monitor the internal condition of geotechnical assets. And I think the medical analogy is useful here. Medical imaging has transformed medicine because it allows the doctors to look spatially and volumetrically inside the human body, minimizing or reducing the need for costly or dangerous operations, allowing, if you like, disease processes to be targeted at an early stage. And really we're seeking to do the same thing with geophysical technologies for geotechnical assets, to non-invasively and volumetrically image inside assets to try and detect problems at an early stage. And on the right-hand side of the overhead at the bottom here, we have an example of 4D imaging of drainage through an active landslide system, where we've been able to link subsurface moisture dynamics and build up with failure events, thereby moving towards more of an early warning system. So in terms of the technology, I want to introduce ERT, or electrical resistivity tomography. The property that we're looking at is resistivity, so the resistance of the ground to passing an electrical current. So why use ERT in this context? Well, firstly, it provides volumetric information. Here we have an image through a railway embankment where we can see structures within the embankment, and this was generated through deploying sensors, just small stainless steel pins at the ground surface, allowing us to see many meters into the subsurface. Resistivity itself is sensitive to compositional variation, so we can use it to distinguish between, for example, clay, sands and gravels, and man-made materials to reveal the structure of the subsurface. Crucially, for these purposes, it's very sensitive to moisture content changes. So as we increase the moisture content within a soil or a rock, so the resistivity decreases as it's easier to pass an electrical current through a wet material. So it's used to monitor moisture content changes. So the PRIME concept is shown on this next slide. On the bottom right-hand side, you can see an example of a sensor array deployed, in this case, on an embankment. These sensor arrays are permanently or semi-permanently installed and connected to our PRIME instrument, our measurement device, which in turn is controlled using the wireless mobile network. So we use the GSM modems to operate the system remotely. So we can schedule measurements, we can retrieve data, and then we go through a processing workflow. So from our electrical measurements, we can extract movement information if there's been ground movement, if we're monitoring a landslide, for example, or unstable slope, we can extract displacement information. We can generate our images of the subsurface, our resistivity images, By applying appropriate calibrations, we can convert our resistivity images into images of moisture content, and then use this information to inform, if you like, asset owners or stakeholders. So in terms of progress, the hardware has now been developed under the ERIIP funding. For the processing workflow, all of these steps we can do and do routinely. For our latest ERIIP project, we're fully automating this workflow. That's the final challenge, if you like. And then in terms of information delivery, in partnership with ITM Monitoring, we've developed a dashboard for delivering this information for the purposes of decision support. In terms of what the system looks like, we house the instrument in a very small GRP enclosure, much like many of those you see by the road or rail sort of network. Battery powered, so it's a 10-watt system powered by a solar panel and communicated to using a GSM router and antenna, as shown there. And then the sensors are deployed in the vicinity of the box, either as grids or lines of electrodes that can stretch many hundreds of meters, depending on the area of ground that needs monitoring. We have a number of test sites being developed across the UK, as shown here. Those that are underlined have been installed and are operating as we speak. The others are due to be installed in the next few months. And I want to just take 3 of these as an example to you. Of the prime system in action. And the sites I'm going to illustrate to you are site 1, 2 and 8. So a railway site, a canal site, and then a water utility site. So beginning with the railway site, we've installed the system on a railway cutting provided by Network Rail, an operational setting, electrified railway line. It's a site that's had a history of instability and displays a mixture of vegetation, something Network Rail are interested in understanding how vegetation impacts on drainage and moisture. Here you can see the sensor arrays being installed on the toe of the cutting and further up. And here we have the prime system sitting at the top of the cutting, just there. Okay, so this next animation shows a LiDAR scan of the area that we've installed into. You can see the enclosure sitting at the top of the cutting. The sort of stepped back feature just below the enclosure represents an old landslide in the cutting. And as we pan around, you get a feel for the site. We've got wooded areas either side of the enclosure and the old slip, and then the slip itself just has grass, a grass cover. And here you can see if you like, the baseline images generated from the prime system showing significant subsurface heterogeneity. It shows the location of the sensor arrays. So a 100-meter section of the cutting. And on our next slide, you can see the same data, but in a slightly different view. And what I'm going to show you now are a time series from this site. And if you look at the graph at the bottom, you'll see the red bar moving along the time axis. So the installation occurred in summer of 2015. And what we're going to do now is see a differential image showing how resistivity changes over time, red representing a drying out and a blue a wetting up. So as we move into the autumn, we can see a wetting front develop across the surface of the site, penetrating more deeply in the wooded area. So we're getting much more dynamic moisture conditions in the wooded area compared to the grassed area. And what we can also see is at the bottom, towards the east, we get a preferential wetting up of the toe of the embankment. You can see much more moisture infiltration there than further along. Then as we move into the summer of 2016, it was a far wetter summer, so there's not much drying out. We only see drying out towards the end of the summer here. But what we can see from this is the impact of vegetation in terms of infiltration and water dynamics. And we've also identified an area of preferential wetting up of the toe, which we've been on further investigation. We've linked back to poor and broken drainage further up the slope. Second example is from Langwinider, so in the Brecon Beacons on the Monmouthshire to Brecon Canal, which runs through the village of Langwinider, as shown here. Our test site, provided by the Canal and River Trust, you can see in the little square rectangle there. So a 200-meter section of embankment, canal embankment, that is in particularly poor condition. which is why it's provided by the Canal River Trust for us to monitor. So if we zoom in, we can see the canal in blue. We can see the towpath immediately to the north of it, and the shaded area that the towpath is sitting on represents our embankment. So the canal is sitting on a hill slope, dipping to the north towards Grove Cottage, and the embankment is keeping the water into the canal, if you like, on the downslope side. 3 known leakage areas were identified within this area. There are probably more. Not all of these leaks could be observed at the surface. Some of them were only expressed sort of in the subsurface. We installed a monitoring array along the tow, attached to the prime system sitting on the towpath. So here we can see the sensors going in at the toe of the embankment, the prime system being installed on the towpath. And then after installation, all that could be seen of the system was the little enclosure sitting on the towpath. All the sensors we buried just below ground level for protection, to avoid vandalism or animals chewing through cables, etc. Halfway through our monitoring period, the Canal River Trust drained the canal and remediated it, allowing us to look at, if you like, a leak to a no leak situation. Really, this allowed us to test the sensitivity of our situation of our system to changing leak conditions. So here we have our baseline scan shown at the top, and the 3 areas of low resistivity shown in blue already reveal our leak locations. Low resistivity is due to high moisture content. What I'm going to do now is show you a time series again. So as we move through from summer of 2015, we have various rainfall events, so we can see a wetting front develop in blue across the surface. But as we move into the winter, we can see this wetting front strengthening and the entire subsurface wetting up. But what we see in our leak areas is relative to the summer of 2015, we see a drying out, so the sort of red, if you like. And this is telling us that even though it's the middle of winter and everything else has wetted up, these areas in relative terms have dried out. And that's because our leaks have stopped, and so the saturation levels are decreasing. So we've shown from this site that we could detect the leakage. We've provided information on the location and size of the leaks, and we've provided this on a daily basis. Usually in the canals, there's only an opportunity to walk over the sites every few weeks or months. But this is providing daily information, and we operated this site remotely and without mains power. And just a final brief example looking at mains water pipe leakage. At the Bristol Water Test Site in collaboration with Birmingham University, we installed to standard sort of specifications a mains water pipe at the test site and engineered a leak into it in the centre of the pit there, and that we could turn on and off. We used a prime monitoring grid of electrodes and system to monitor various leakage experiments. And here we have an example of a 3D view of one of those experiments. And as I progress through the time axis at the top right-hand side, here is the point at which the leak was turned on, and you can see this very clearly in the prime image, 1.5 litres per minute. You see the leak develop, the subsurface wet up. And then at this point we began to turn the leak off, and you can see a return to background conditions as the leak dries out. So just to summarise, we've developed a new geophysical remote condition monitoring technology called PRIME. It provides near real-time information on the internal condition of assets. It's low cost and low power. It complements conventional point monitoring techniques, and we've demonstrated it in a range of different settings with infrastructure stakeholder partners. Ongoing development is focused on fully automating the information delivery side of things and generating new case histories. And within the next 12 months or so, we hope this technology be ready for commercialization. And lastly, by way of industry endorsement, the PRIME system won the Ground Engineering Award in the summer for product and equipment innovation. So that's me done, and thank you for listening.
Thank you, John, for your presentation. I will now hand over to Professor Simon Mott. Yes. So Simon Matt is a professor of Earth surface processes within the School of Geoscience at the University of Edinburgh. He has degrees in geology from the University of California, Berkeley and University of California, Santa Barbara, and received a PhD in environmental engineering from the Vanderbilt University. Since 2007, he's been academic staff at the University of Edinburgh, exploring landscape response to both climate and tectonics, and has developed software to explore both earthquakes and landslide hazards. So over to you, Simon. Can you hear us now?
I can hear you. Thank you.
You can hear us now.
Can you see my screen?
Yeah, we can see your screen as well.
Okay, brilliant. So today I'm going to talk about a project that I've been involved in with the partners that you see at the bottom of the screen. We are taking a topographic approach to look at landslide risks, and I just want to acknowledge Stuart Grieve, who is the postdoc on this project. So why do we focus on topography? One of the reasons we focus on topography is because infrastructure assets can span thousands of linear kilometers. So what John showed was an amazing approach. I thought that was really interesting. But installing at specific sites can be quite expensive. So how do we understand risks at kind of a national scale? Because we can't do site investigations everywhere. So the purpose of this project is to try to identify efficient ways of identifying risk areas. I just want to make really clear that what we're trying to do is no substitute at all for site investigations, but it's more of the first iteration of this process whereby you can then send more site-specific investigations or investigators into the field. So I just want to go through a few examples of areas that we've looked at some of the topographic drivers of landslides. So the first place I'd like to look at is Watford. So actually, if I go back a slide, so this was a landslide that happened near Watford in a railway cutting. And it caused quite a lot of delays for Network Rail. So we wanted to just get a sense of the risks involved, and could we have identified that as a kind of high-risk place beforehand. So what we do is we take topographic data, and we then run some numerical models of hydrology and flow routing. So there's flow routing algorithms, and then that flow is then propagated into a stability model, which balances the frictional forces against the downslope forces, and we try to come up with places that seem to be at risk. So this is a map of the hydrology that was derived from a 1-meter topographic map of the Watford site. And in a second, I'll show you our kind of best estimate of the landslide risk at this place, or at least the hazard at that area. But the thing that I want you to notice here is that we've spent a lot of time trying to get these limit equilibrium models to work, and really one of the biggest drivers to whether or not it can get a good picture of where you might get a landslide depends on the topographic data quality. So this is a 1-meter LiDAR image of this site, and I'm going to overlay, so actually before I get to overlaying a lower resolution DEM, this is our limit equilibrium, and you'll see the kind of red star is where the landslide occurs. So actually the dark red just there to the southeast of that red star is where the landslide actually occurred. So in this case, the highest risk is actually located on the actual failure site, but that's almost entirely driven by the runoff map that I showed in the previous slide. If I look at the next map data, so that's a 5-meter topographic data set that is our only current UK-wide high-resolution data set, although Ordnance Survey also has a 5-meter product. But those two products are not as high resolution as this, and I'll show you the same area at that resolution. This is what the 5-meter resolution looks like. And basically, it doesn't concentrate flow anywhere near that failure site. So really, we're quite restricted by our access to good topographic data. So I'll show you the next site. So this is in Derbyshire. It's a site along the A57, and it suffered a failure a few years ago. That was investigated by British Geological Survey. So we went here to try and also understand if topographically there was anything interesting going on. Again, what you're looking at here is the next map data. So this is 5-meter resolution data. It has some artifacts that are a byproduct of the data processing that has gone into this topographic map. But basically, the other 5-meter data products are similar to this. And so we can look at the sort of limit equilibrium models that we see here. If we try to tune some of the models with different scenarios of vegetation, I'm just going to show you some images initially with no vegetation in it. The vegetation can add to the cohesive strength of the near surface materials. So we take our best guesses of root cohesion. In this case, the root cohesion is 0, but what our model does is it tries to tune the root cohesion to observe landslides, and if we don't have that, then we try to use published numbers for root cohesions. So this is kind of a typical map in that what we end up with is a lot of false positives. So almost the entire landscape lights up in red in this case. So this is partially down to the fact that the root cohesion is too low, but it's also down to the fact that with a lower resolution DEM, you get sort of quite a bit of noise in the analysis. If we go to a higher resolution topographic map, again, this is with no vegetation whatsoever, but you can actually start to see a better understanding of where you might get some landslide risks. So if we also look at the flow accumulation, again, we find this to be quite different between LiDAR data sets, high resolution 1-meter resolution data sets, and 5-meter data sets. So this is flow resolution, flow accumulation from the next map, 5-meter data set, and the red star is where there was an event. So you see almost no water leading to that event, or no flow accumulation. But if you add the LiDAR data, what you see is quite a lot of obvious flow accumulation onto the road and in the area of where you got the land movement. So what we find, and this also comes out in our conversations with our colleagues at Transport Scotland, the Network Rail, and Forestry Commission, oftentimes the sites that tend to lead to failures are where water has been routed onto a slope that then leads to instability, and on the 5-meter resolution data you can't see any of that detail. So this is sort of a plea to try and get better and higher resolution data across the UK, because it really makes a big difference in our ability to see where these slopes are at risk. Again, this is a minimum root cohesion model on the next map data, and you get very little highlighted sites, although there are some sites that have been highlighted as risky. And we also have another method that we can use. So in one method, we look for kind of slope stability of shallow slides, but we can also look for areas that are particularly topographically rough, and that can give some sense as to older, deeper slides. Again, this is only as good as the topographic map. So if you look to the northeast corner of this map, you'll see a kind of triangulated bit of topography. That's because the data resolution is lower there, and basically we're not really able to resolve any of these patterns using the lower resolution data. One of the things we became interested in was trying to use our flow routing algorithms to try and map the upslope areas of influence onto segments of infrastructure networks. So what we do is we use a segmentation type of algorithm to split the linear features, such as roads or rails, into segments, and then we can look at all the pixels that drain onto those segments, and we can calculate the probability of having cells that are risky in terms of having a kind of higher chance of being prone to failure. So the purpose of this is that what we can do is, if we have powerful enough computers, we can then run this for the entire infrastructure network, and it becomes kind of a question of computational power in order to do that. So if given the time and the computational power, we could do this for the entire infrastructure network of the UK. That hasn't been done yet because it's quite computationally intensive. I just wanted to show as well a site from Scotland. So this is near Loch Ness. It's a site that the Forestry Commission was interested in. And one of the things we looked at here was trying to get a bit more granular information about the root cohesion. So our intention was to, in collaboration with Forest Research, try to collect data as to tree types and use that to drive some of these limit equilibrium models. So in this case, this is again one of these maps of relative slope stability, again calculated by this limit equilibrium model. And in this case, we have no cohesion, and it's not very useful. You get the entire landscape to light up as in sort of unstable. As you start to go through the literature for maximum root cohesion, you tend to highlight more focused areas that are at risk. But to us, this wasn't quite as interesting as our efforts to integrate some of the Forest Commission data. And actually, I've just got one more slide. So if you have the minimum root cohesion, you get quite a different picture of what is risky. So we really are trying to do quite a bit better than these two things, because if you're an infrastructure owner, the first slide, you have a very limited amount of places that you really need to go and have a look at, whereas if you have the minimum root cohesion, the entire landscape lights up, and really you can't explore the entire landscape. So we need to try and do a bit better as to constraining what the proper root cohesion is. So one thing that we've tried so far, and I think this is still under development, but we are working on our software to ingest the land cover classes, which we get from Forestry Commission. At the moment, the metadata for these layers is not quite as easy as we hope, so we're trying to write some software to convert the various types of data, GIS data layers that we get. But at this stage, for this site, we can take Forestry Commission data and then break the forest into the dominant tree type. So we've got and land cover type. So in this case, we've got sort of 5 vegetation classes. Each of these vegetation classes, we've gone into the literature and found the root cohesion values that have been measured by others in the field, and this gives a sort of more nuanced view of where you might have potentially hazardous slopes. So what we'd like to do in the future is try to constrain this a bit more with our collaborators at BGS, because they've got the best landslide database in the UK, and try to test if this is actually getting better results than just a simple root cohesion model. And I think another thing we hope to do in the future is, because the Forest Commission and private landowners use different planting strategies, If we are able to tune the root cohesions to our actual landslide records, we can then better inform the infrastructure owners based on if the planting type or the land management in forested landscapes changes, what sort of effect might that have on the relative hazard associated with landslides. So that just brings me to my conclusion slide. So the main thing that we found from this study is actually we can spend a lot of time writing software, but the predictions are really only as good as the topographic data that underlies our analysis. Right now, we do have LiDAR for bits of the UK from the Environment Agency and the Scottish Government. Those high-resolution topographic data sets tend to be associated with flooding. So they stay in the river valleys, but that's not really of too much use for landslide studies. So what we really need is LiDAR that goes up onto the hill slopes. We cannot replace site investigations with this technique. It's because we have far too many false positives. But what we can do is create spatially distributed maps of the relative risk to linear features of infrastructure, and then that can be used to drive planning decisions on where to carry out site investigations. So it's really a tool to highlight the risky areas that are not currently known to have failed in the recent past. And with that, I will conclude. Thank you.
Thank you, Simon, for presenting your approach and your project. I will now take back control, and we can then move on to the Q&A session. So thank you again, Paul, Jonathan, and Simon for your presentation. And again, I would encourage the attendees to use the question tab on the right-hand side of the screen in the control panel to send their questions to the speakers. And if also include in your question, include the name of the speaker you would like to address your question to. So let's wait for the questions to come in. Okay, so one of the questions is whether you are also, I think this is for Jonathan and Simon, whether you're also working with other industry partners that are not specifically for the transport sector. So I saw from your presentation, Jonathan, that you're also working with the utilities. I wonder whether there are ongoing conversations with other infrastructure sectors.
Yes. So we're working with National Grid, for example, looking at substation stability. We're beginning to talk to some of the water companies, particularly in the area of dam safety. But I would say that this sort of technology, prime time technology, is applicable to any sort of near surface problem where moisture dynamics, contamination, pollution might be an issue. So yeah, it certainly goes applications go way beyond transportation.
I'll just mirror that comment. So we're focused on Transport Scotland and Network Rail, and we've mainly been talking with Forestry Commission. But again, these techniques are applicable to sort of any infrastructure that is on a slope that is at risk from a landslide. So it's really not industry specific, I would say.
Okay, great.
And just to reassure everybody, Transport Scotland is also talking to Forestry Commission, as there are obviously close interactions between forested areas and roads through those areas.
Thank you, Paul. A question from Sarah. This is a question for Simon. Have you taken account of geology in your stability models?
So our model does have the ability to have a layer of geology in it. The main forcing on that is because we're not trying to model rock falls at the moment. Our software doesn't do this. It's shallow landslides. So it's really the soil properties that are important. But based on the geologic, the underlying lithology, you tend to get quite a difference in the soil thickness, which plays a role in the stability. So at the moment, what we are trying to do in specific sites where we have the data is use some of the superficial geology layers from BGS. So that does play a role. Again, it's quite difficult to integrate because it's hard to know if those the soil thickness is quite heterogeneous. So basically, it leads to a lot of uncertainties in how those groundwater models propagate through our slope stability analysis. So we try and take a probabilistic approach instead of knowing exactly how thick the soil is. But we can integrate those other data layers.
Okay, another question for you, Simon. You're looking at cohesion routes. So are you looking at very shallow 0.3 to 1 meter depth failure models then?
That's right. They tend to be for the shallow landslides. We've tried to get some software working that works for deeper landslides. So some of our roughness algorithms are better at detecting deeper landslides, and we also have some pore water models that tend to do a bit better at deeper landslides. But those to test that kind of those models, we're going to need more of the sort of data that Jonathan produces. So to try and correlate the rainfall record with recorded motion. So I would say that's still quite early in the development stage.
Okay, thank you. A question for John. Could ERT be applied to areas of karst dissolution risk?
Theoretically, yes. I mean, where you have cavities opening up in the subsurface, you will get a contrast in electrical properties, which is what you need to image these things. It depends on depth below ground level. If you're deploying this technique using surface-based sensors, then you're going to be limited in how far down you can see. So we've used, for example, cross-hole imaging to look for deeper cavities where you need a deeper resolution. But in principle, yes, you could use this sort of technique for that type of process. And in fact, there are examples in the literature, in the research literature, where this has been done.
Okay, another question for you, John, and also I think for Paul. A lot of interesting points and appears to be retrospective. How are these being integrated into new designs? I'm thinking about the application of Prime onto Transport Scotland jobs.
So,
who wants to
go first, John?
I should emphasise that this technology is still in the R&D phase, although it is progressing rapidly towards a point where it will be commercialised. We're not yet at the stage where we have, if you like, sort of fully commercial demonstrators where it has been integrated with other approaches and systems. I should make the point that the dashboard that we've worked with ITM monitoring is an industry standard information delivery dashboard, and part of our reason for using that was that it was already established for geotechnical applications. So I don't know if Paul has anything else to add.
Well, I was just going to observe that the sites we are particularly interested in, like Rest and Be Thankful and Glen Ogle, are of a scale which I suppose to some extent is in between the scale that Jonathan is working at and the scale that Simon is working at. They're a couple of kilometres long, and I can see it instrumenting a slope of that size could be very difficult. So we're not quite there yet. And also another factor is that that land is in private ownership. Transport Scotland only actually owns the land immediately adjacent to the road itself. So all the works that we have done at Brecon Beacons have been with the agreement of the landowner, and we've had to take him on board and take him along with us. So there are a number of practical difficulties in trying to establish an instrumentation set for the whole slope. But we're certainly interested in what Jonathan's been doing, whether that could be rolled out to the next sort of scale up. I'm not quite sure.
Okay, thank you both. Conscious of time, I'll just take this last question for Simon on the reliance on topographic surveys. So Kenny asks, I assume these are based upon seasonal constraints. Do these need a baseline dataset to be established?
Yes. Yes, the short answer to that is yes. I mean, really, once we have a national topographic data set, I think, so a LiDAR data set at 1 meter, and that means not just in our floodplains, but going up onto the hill slopes, I don't think there's going to be quite as pressing need for repeat surveys. So you might do targeted repeat surveys, but I think the key is to try and fly the entire country. And I know that in Scotland there's some talk about getting nationwide LiDAR coverage, and the Environment Agency continues to fly LiDAR, but right now we could be doing a bit better than we are, because it really makes a huge difference to our ability to predict both flow and landslide risk. But as you can collect that data through the seasons and end up with that a national baseline data set.
Okay, thank you. Okay, thank you all for your presentation and for answering to the question that the attendees asked you. Before closing the webinar, just some information that might be useful. So the slides and the recordings will be available on our website after the event. And we are also organizing other ERIIP webinars and events, and you may want to have a look at our website in the near future for further details on those. There are also other events that may be of interest to you that Syria is organizing. So we currently are managing an infrastructure resilience series of events. The next events will be in March, infrastructure interdependence in practice, and in April, justifying investment in resilience. And there will be in April another event on green infrastructure as well. In terms of the ERIIP program, if you want to know more, find out more, please visit again our website or NET's website. Finally, thank you again to the speakers, to Paul, John, and Simon for their time today, and thank you again for attending the webinar. If you have any questions and want to know more about the projects or about the program, please feel free to contact me. The email address is on the screen. Thank you and have a good day. Bye.
Thank you.
Thank you.
Thank you.